Quantum tunneling. At the heart of reality exists a rule book, an unchanging set of fundamental laws governing the universe's behavior. These laws remain steadfast, trustworthy, and largely predictable. Drop a ball, and down it goes. Heat travels from hot to cold. A brick wall halts your movement. Yet, beneath this outwardly stable reality, deep within the quantum world, things begin to behave oddly. Particles break the rules. They flicker, blur, and at times do something truly astonishing. They pass through barriers as though those barriers don't even exist. This bizarre phenomenon is called quantum tunneling, one of the most peculiar effects in all of physics. Picture standing before a mountain. You might spend years climbing it or tunneling beneath it. But in the classical world, the domain of large objects ruled by Newtonian physics, you'd never just pass right through it. However, in the strange realm of quantum mechanics, particles can and do exactly that. Electrons, protons, even entire atoms have been seen performing this seemingly impossible escape. But how is this possible? And even more curiously, does this quantum magic have limits? To grasp tunneling, we must first understand how particles behave in the quantum world. In our ordinary, daily experiences, particles are distinct and well-defined, like a marble on a table, which is clearly here or there. But in the quantum domain, particles show a dual behavior. They act both like particles and like waves, which goes against our natural understanding. Instead of having a precise location, a quantum particle exists as a probability wave, a kind of mathematical fog representing all possible positions. Imagine throwing a stone into a pond, ripples spread outward. Similarly, a quantum particle's wave function spreads through space, reflecting the chance of locating that particle in various places. Now imagine placing a wall in the path of those ripples. In classical terms, the ripples would stop at the wall. But in the quantum view, the wave function doesn't entirely disappear. It seeps through. On the far side of the wall, a faint ripple remains, suggesting a small chance that the particle can tunnel through the barrier and emerge where it logically shouldn't. This isn't mere theoretical speculation. Quantum tunneling powers some of the universe's most crucial processes. Inside stars, hydrogen nuclei overcome their natural repulsion and fuse, releasing energy as light and heat. According to classical physics, the repelling positive charges should prevent fusion. Yet, due to quantum tunneling, these particles slip through energy barriers, allowing stars to radiate. On Earth, tunneling underpins technologies like scanning tunneling microscopes, letting scientists observe individual atoms by leveraging electron tunneling. It also plays a role in flash memory, where electrons tunnel through insulating layers to retain data in your phone or computer. But as astonishing as quantum tunneling is, it has limitations. For tunneling to occur, the barrier can't be too thick or too tall. There must be some non-zero chance of reaching the other side. As the barrier increases in size or height, the odds of tunneling fall off exponentially. So, tunneling isn't a magical shortcut around physics. It's like rolling infinite dice and hoping for a miracle outcome. Still, physicists continue to test tunneling's boundaries. Across labs worldwide, scientists have successfully tunneled entire molecules and atom clusters through barriers, stretching the limits of what seems achievable. Could even larger things tunnel? A virus, a human cell, or even a whole human being? In theory, yes. In practice, almost certainly not. The wave function of something as complex as a human being is unimaginably tiny. The probability that every particle in your body would tunnel together at once is so absurdly small, it's practically impossible. You'd have better luck recreating Shakespeare's Hamlet by tossing Scrabble tiles into the air. Even at the microscopic level, tunneling isn't fully understood. Scientists are now probing how long tunneling takes. Is it instantaneous? Or does the particle traverse the barrier gradually? Experiments using ultra-fast lasers hint that tunneling may occur quicker than previously thought, possibly even instantly. Yet this remains a mystery, one still lurking on the edge of human understanding. There's also a deeper question. Could tunneling reveal something fundamental about the universe? Might it hint at hidden dimensions or uncover new physics? Some physicists think tunneling might offer a glimpse of the elusive theory of everything, a single framework uniting gravity, quantum mechanics, and the universe in one elegant equation. At its essence, quantum tunneling is a powerful reminder of the universe's deep strangeness and beauty. It tells us that at quantum scales, reality isn't solid or predictable. It's fuzzy, probabilistic, and full of mystery. Particles ignore the boundaries we take for granted. They blur the lines between here and there, between what exists and what doesn't. So next time you gaze at a distant star's light or save a photo to your phone, remember this. Somewhere in the depths of reality, particles are breaking the rules. They're sneaking past barriers, challenging expectations, and showing us that the universe is far stranger and far more magnificent than we ever imagined. And maybe, just maybe, within the limits of quantum tunneling lies the key to our next great discovery about reality. The real question isn't if something will tunnel through that last wall, but when. Proton decay. In the silent depths of time, below reality's surface, where protons and neutrons weave the universe together, a quiet clock might be counting down. This clock is so faint, so slow, it is nearly impossible to perceive. Yet, it's a countdown embedded within every atom in your body, every molecule of water, every shining star above. This is the question of proton decay, among the most profound unsolved mysteries in modern physics. Protons serve as matter's foundation. They are the core of atoms, securing electrons in their orbits and shaping everything we see and touch. For all practical intents, protons are ageless. They don't deteriorate, and they don't fall apart, at least according to what we currently understand. But suppose that assumption is wrong. Suppose that, over enough time, even protons, the very building blocks of reality, would disintegrate into something else. If this is true, if protons do decay, it carries significant meaning. It implies that the universe isn't grounded in permanence. Even the most basic forms of matter would have an end point, an expiration, a moment when their structure fails, and they dissolve into more delicate, ghostly particles. That means everything, every atom, every star, every galaxy would ultimately fade into oblivion. Here's the twist. Despite years of searching, a decaying proton has never been observed. To grasp the weight of this mystery, we must return to reality's most basic components, the standard model of particle physics. This model is our best framework for explaining how the universe functions at its tiniest scales. It introduces us to quarks, leptons, gluons, photons, and to the unseen forces binding matter together. Within the model, protons are considered indefinitely stable, but physics doesn't end with the standard model. Some theories aim to go beyond. attempting to merge the universe's fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces. These are known as grand unified theories, or guts, and according to many of these, protons can decay. Picture a lone proton resting in an atom's core. In the moment of its decay, an event so uncommon it might occur only once every 10 circumflex 34 years, it would abruptly convert, releasing a shower of rare particles. The specifics depend on which gut you use, but one recurring idea is that the proton transforms into a positron, a positively charged electron, and a neutral pion, which rapidly decays into gamma rays, flashes of light. The death of one proton would be nearly indetectable, a brief flicker, a soft sigh in the darkness. But scaled up across every proton in every atom across the cosmos, it could mean the gradual unraveling of all matter. Here lies the issue. This process has never been seen. Physicists have constructed massive underground labs in search of this elusive decay. These labs are buried deep beneath the surface, protecting their detectors from cosmic radiation and other background noise. One example is Japan's Super Kamiokande experiment, a vast tank containing 50,000 tons of ultra-pure water, hidden deep beneath a mountain. Thousands of hypersensitive light detectors surround it, always watching, always waiting, hoping to catch the brief glow of a proton's last breath. Years have passed, decades, even. Still, nothing. So, does this mean protons are truly immortal? Or is it that we haven't looked the right way yet? Perhaps the theories we rely on are incomplete. Perhaps protons do decay, but by means we don't yet understand, or across spans of time far exceeding what we're capable of observing. The quest to understand proton decay goes far beyond the particle itself. It's about the destiny of the universe. If protons are stable, then matter might theoretically last forever. Stars may burn out. Galaxies might drift apart. But the protons would endure. Silent, timeless, scattered particles floating through space's endless dark. If, however, protons decay, then the universe has an end game. An inconceivably distant future awaits, long after the stars have died and black holes have vanished, where the cosmos's final act becomes the slow, quiet decay of protons. Atom by atom, molecule by molecule, all matter would dissolve into radiation, vanishing into a cold mist of neutrinos and photons. The implications are staggering. The timeline is almost unfathomable. And yet, physics finds beauty even here, in dealing with spans longer than the universe's current age, in chasing whispers so faint they brush the edge of detectability. Still, we search. But why? Why devote lifetimes, spend billions, invest decades in the pursuit of something so fleeting, so intangible? Because answering the question of proton decay is about more than particles. It's about understanding our universe, our reality, and our role within it. If protons decay, it reveals a cosmos that isn't still. It's dynamic. It's in motion, evolving over scales far larger than human existence. And if they don't, if protons are forever, we must ask why. Why are they so stable in a universe where change is the only constant? Every quiet experiment in an underground chamber, every captured photon, every chalkboard theory, they all contribute to one larger question. Are the rules of reality fixed? Will the universe conclude in finality, or will it drift endlessly in unchanging stasis? Somewhere within the experimental noise, or within yet undiscovered equations. The answer waits. Maybe it's hidden in a single flash of light deep underground, a hushed whisper from a proton's death. Or perhaps it lies in a theory still unimagined, a new structure that will transform our understanding completely. But for now, the protons within you remain, still, silent, holding your atoms in place, shaping the world around you. Yet somewhere, maybe in a remote star, maybe underground, maybe drifting in the void, a lone proton may already be counting down its final seconds. The holographic principle. Take a moment to imagine that everything familiar to you, the stars, galaxies, planets, and even your own existence, might not be exactly what it appears. The universe, with all its boundless beauty and complexity, may not be a three-dimensional realm stretching endlessly into infinity. Instead, it could be something much stranger, something flat. Reality itself might be projected onto a two-dimensional surface, much like light beaming through film onto a movie screen. This isn't a scene from science fiction. It's the holographic principle, an idea from theoretical physics that is both deeply profound and incredibly mind-bending. This principle resides where black holes, string theory, and the very nature of space and time intersect. And it all originates from a disturbing insight about information and the peculiar characteristics of black holes. But let's not rush. To see how physicists arrived at this principle, we must begin at the boundary of a black hole. In 1974, physicist Stephen Hawking made a revolutionary finding. Black holes are not completely black. They release a faint emission, now called Hawking radiation. With time, this radiation causes the black hole to shrink, and eventually, it disappears entirely. However, this revelation presented a troubling paradox. What becomes of the information from everything that fell into the black hole? According to the laws of our universe, information isn't supposed to simply vanish. If, for example, you burn a book, the pages may turn to ash, but the information within, the text, the ink, the arrangement of letters, isn't truly gone. In principle, with enough understanding and computing power, it could all be reconstructed from the resulting smoke, heat, and ash. This concept, that information cannot be destroyed, is central to physics. Yet, if a black hole evaporates entirely, where does all that information end up? This conundrum became known as the black hole information paradox, and for many years, it troubled physicists. One of them was Gerard 't Hooft, a Dutch theoretical physicist and future Nobel laureate. In the 1990s, 't Hooft put forward a radical possibility. Maybe the information entering a black hole isn't lost. Perhaps it is stored on the event horizon, the black hole's boundary. Picture a three-dimensional object being pulled into a black hole. Rather than vanishing into the singularity, its information might instead be captured on the event horizon surface, similar to a shadow cast on a wall. This idea was groundbreaking. It implied that everything occurring inside the black hole could, at least theoretically, be represented by data imprinted on its two-dimensional boundary. But what if this wasn't unique to black holes? What if the same concept applied to the entire universe? Enter Leonard Susskind, a theoretical physicist who expanded on 't Hooft's idea. Susskind suggested that our universe itself could follow this principle. Everything we observe in three dimensions might actually be encoded on a distant two-dimensional surface, some kind of cosmic horizon at the edge of our observable universe. To say it simply, our seemingly three-dimensional reality could be a hologram. Now, Before letting that idea overwhelm you, let's clear up what it implies. The holographic principle doesn't claim that the universe is fake or an illusion, as in the Matrix. Rather, it proposes that the most fundamental description of reality could be much simpler than it appears, that this immense, limitless cosmos could be fully described by data inscribed on a two-dimensional surface. But how is that even possible? How can a flat, two-dimensional plane explain a three-dimensional universe? Think of a holographic image on the flat surface of a two-dimensional film. It is possible to store information that creates the illusion of three-dimensionality. If you move around a hologram, you perceive depth, motion, and perspective. The image isn't in the sheet, it is projected from it. Likewise, the holographic principle suggests that what we experience as three-dimensional space, our sense of depth, motion, and distance, could be an emergent effect of a deeper two-dimensional reality. At this stage, the principle becomes more than an abstract idea. It becomes a tool of immense mathematical power. In 1997, physicist Juan Maldacena proposed a groundbreaking theory, the EDS/CFT correspondence. This theory provided a clear case where the holographic principle works. It showed that a universe governed by gravity in three dimensions could be mathematically identical to a universe governed by quantum mechanics in two dimensions. This meant that gravity and quantum mechanics, two theories that often seem incompatible, might actually be two perspectives of the same holographic phenomenon. This insight shook the world of theoretical physics. The holographic principle was no longer just a theoretical possibility. It became a framework, a powerful lens to help reconcile Einstein's general relativity with quantum mechanics. But it gets even more bizarre. If the universe truly operates holographically, then deep philosophical implications arise. What does it mean to exist in a universe where space and time themselves might not be fundamental? Where everything we sense, what we see, touch, and feel could just be information on a remote boundary? It also introduces a disturbing possibility about reality. If our universe is essentially two-dimensional, then space and time, the backdrop on which all events occur, might not be as real or solid as we believe. They could be emergent phenomena, like ripples on a pond's surface, that conceal a deeper, underlying reality. For now, the holographic principle remains just that, a principle, a fascinating clue in our quest for a theory of everything. Still, experiments, like those at Fermilab's holometer, are actively exploring this hypothesis. Scientists are trying to detect tiny jittery shifts in spacetime, signs of the pixels of our cosmic screen. Regardless of whether these experiments succeed, the holographic principle has already shifted our understanding of the universe. It's revealed that the line dividing dimensions and the boundary between space and information may not be as sharply defined as once thought. It's a potent reminder, reality, no matter how familiar, still holds mysteries that feel like science fiction. So next time you gaze at the night sky, watching stars and galaxies spread across unimaginable distances, remember, there's a possibility that everything you see is simply projected. Theory of everything, also involved in one of the greatest cosmic puzzles of all time. Dark matter, actions, with their ghostly properties and incredibly weak interactions with ordinary matter, play a key role. They are prime candidates for the invisible mass that holds galaxies together. Yet, the action's potential goes beyond that. These elusive particles might even influence the fundamental constants of nature themselves. In certain theoretical models, actions could function as cosmic dials, subtly tuning constants, such as the fine structure constant, which dictates how light interacts with charged particles. If actions can vary through space and time, then constants might not be so constant after all. Astronomers have already started looking for signs of these cosmic dials. They examine distant light from quasars, ancient beams stretched across countless light years and billions of years. If the fine structure constant differed slightly billions of years ago, its signature would be imprinted into this ancient light. And in some studies, hints have emerged. Tiny deviations, anomalies that refuse to disappear completely. Still, these results are not definitive. The search for actions goes on. In laboratories located deep underground and shielded from cosmic noise, scientists rely on magnetic fields and ultra-sensitive detectors in their attempts to capture the faintest whisper of these ghost particles. Each experiment brings us closer to an answer, but thus far, the axion remains elusive, a faint silhouette on the horizon of our understanding. If actions are discovered, they could address long-standing puzzles in particle physics and cosmology, and simultaneously challenge our assumption of a static, unchanging universe. They might show that the constants of nature, those we consider fundamental and eternal, are actually dynamic properties, shaped by the universe itself. For now, the search continues, within magnetic traps, across distant starlight, and through mathematical models. The axion remains one of the most tantalizing possibilities in modern physics, and with every experiment, every flicker of anomalous data, we move a little closer to one of two outcomes: uncovering this elusive particle, or rewriting the very rules we believed the universe was built upon. The pioneer anomaly, far beyond the planets of our